Let's start. I'm very glad to present Sanjay Reddy. He's a full professor at the Washington University and a member of Institute for Theoretical Physics. Oh, actually, sorry, INT, Institute for Nuclear Theory in Seattle. He got his PhD in '98 from Stony Brook. He had several postdoc positions, actually maybe one in Seattle at Washington University. He then was a fellow in Los Alamos at Los Alamos National Lab. Not sure the official title, I assume it's scientist. And he joined Washington University in 2011, moved through all the ranks, and now he's a full professor working on astrophysics, nuclear, neutron stars, a lot of cross-disciplinary physics, and I'm very glad that he agreed to give his presentation here in Theoretical-Physics-Colloquium. So with that, you may start.
Okay, thank you, Igor, very much for this invitation. And yeah, these are interesting times, and these Zoom meetings and.
If you'd like, you could use your video. I will stop my video.
Okay. So these are certainly interesting times, and these Zoom meetings and talks, keeping things interesting. So I wanted to share with you some of the excitement in studies of neutron stars as we enter this era where multi-messenger astronomy, nuclear particle physics, computational astrophysics, and a very vast and generous universe that we are being able to observe using multiple sources, which we see in multiple messengers, where the telescopes such as radio telescopes, optical telescopes, X-ray telescopes that's been around for many decades are now watching neutron star phenomena in unprecedented ways. We also have other sources of information which tell us about the structures and phenomena associated with these fascinating objects, such as elemental abundances. Later in the talk, I'll mention how neutron stars are likely the source of very heavy elements. We also have detectors large enough to see neutrinos from galactic supernova, which also involve neutron stars. And in the last couple of years, there's been a great deal of excitement because gravitational waves from neutron stars have been observed, and the prospects to see many more of such events are very good. So in many ways, this is an exciting time, perhaps the best of times we've had to study neutron stars, because neutron stars are perhaps the only sources that we know, astrophysical sources that we know that can provide us all of the messengers with luminosities that are large enough that we can detect them here on Earth. So let me start with the big picture and ask some big questions that, understanding neutron stars and observing them can potentially help us address. For example, we've known for many decades now that very extreme phenomena such as supernova, gamma ray bursts are associated with neutron stars, or at least the central engine has to do with a compact source, such as a neutron star. We've also wondered for some time what are the states of matter at very high density, especially densities encountered inside neutron stars, and can we use theory and observations to actually determine what these states of matter may be. It's also been a long-standing question to address heavy element nucleosynthesis in the universe. Of course, many of us have wondered about what states of matter exist outside of the standard model. Is dark matter a particle, and what might be its properties? The study of neutron stars and its observations has the potential to address all of these questions that are at the forefront of theoretical physics now. So the outline for my talk is as follows. I will give a very brief introduction to neutron stars, and then there are three topics, somewhat connected, but can be independently viewed. The first topic will be neutron star structure. Here I'll talk about mass and radius and the equation of state. Then I'll talk about neutron star dynamics. I'll give you two examples where transport phenomena play an important role. And finally, if there is time, I will talk about how neutron stars can be used as a laboratory to study dark matter. And then I'll have a few words to conclude. So a brief history, it's remarkable that it wasn't physicists, but it was astronomers just a few years after the discovery of the neutron, who came up with this remarkable sentence in a remarkably prescient but short paper. They just said, without any equations or without any justification, that neutron stars are probably very small objects, and that these objects are created when an ordinary star goes supernova. Now, many, many decades later, almost 90 years later, we accept this, but back in the mid-1930s, this was just sheer magic. I mean, it's remarkable. This is one of the most amazing statements in neutron star literature that you can find, where they pretty much got everything important right without even writing down a single equation or using any observations. So there's certainly some extraordinary vision that Fritz Zwicky and Walter Baade exhibited when they talked about this existence of neutron stars. It took many decades, it took almost 35 years since then to discover neutron stars, and we all are aware of that. Jocelyn Bell and Anthony Hewish built a very crude radio telescope by stringing cables around posts, and they discovered very periodic pulses with sub-second periods. And back then, I think there were only two explanations that we could come up with for sub-second periods that were very periodic. Either it was some form of extraterrestrial life that was producing periodic signals, or pulsars, neutron stars that are spinning rapidly. It didn't take long. A few years later, pulsars were identified as neutron stars through the work of people like Gold and others who understood that there may be a beaming of electromagnetic radiation from neutron stars that are rotating and would explain the observed periodicity. Now, for most of us here, neutron stars fascinate us because they probe the phase diagram of very dense matter. And so what's plotted here is a phase diagram where the y-axis is temperature measured in MeV, and the x-axis is measured in grams per centimeter cube. I am a nuclear astrophysicist, so I am allowed to use nuclear units in one axis and astrophysics units in the other axis. So for some of you, 2.5 times about 10 to the 14 grams per centimeter cube is roughly the density of a nucleus. So what this phase diagram depicts is the various phases of matter that are, that are based either on calculations or on observations and experiments. We know that we can probe the finite temperature phase diagram at very low baryon density using heavy ion collisions. And this is the region where one can also do lattice QCD calculations to understand the phases of matter. And there have been many insights in the last 10 years about the states of matter encountered at finite temperature and low density. But neutron stars are probably the only access we have to very low temperature matter at very high density. So here, shown in the figure, are regions where we think neutron stars probe matter. We think neutron star central densities reach at least about 10 to the 15 grams per centimeter cube. And there are regions of this phase diagram that we can calculate. I'll come back to it at low temperature. And there are regions of these phase diagram that we cannot calculate. So regions, that'll be a significant part of the talk, the first part of my talk. There are interesting regions at asymptotically large densities where, because of the asymptotic freedom in QCD, matter becomes weakly coupled, and we have theoretical tools like perturbative QCD and the inclusion of non-perturbative effects such as pairing that one can include at very high density and do reliable calculations. The transition between hadronic matter and quark matter is a very complex problem at finite density, and that's a problem that despite many efforts, progress in addressing that quantitatively has been slow. So let's begin from a neutron star perspective and ask what is dense matter that's encountered in a neutron star, because neutron stars basically take ordinary matter, think of a little chunk of iron, which has a typical density of about 8 grams per centimeter cube, and you compress this matter to extreme densities. So we know that the density of an atom is 8 grams, about 8 grams per centimeter cube, but the density of the nucleus is about 2.5 times 10 to the 14 grams per centimeter cube. So we are fortunate that we have high density material in the form of a nucleus in the laboratory to test our theories and study nuclear matter at high densities. So if we start thinking about compressing matter, starting with low densities, the first thing that happens is the electrons begin to get compressed. And so if we now think about taking a chunk of iron and compressing it to very high densities, we can think of this in the following simple qualitative fashion. The best way to approach compression of matter is to think about what is going on with the degrees of freedom and how their energies are changing as you compress it. So I like to think of this as a tale of frustration and liberation. So the energy to keep track of when you compress matter is the Fermi energy of the most dense component in the system. So between about 10 to the 3 to 10 to the 6 grams per centimeter cube, the nucleus doesn't even realize there's compression going on because it's a very small object at the center of the atom. The object that experiences the compression, the particles that experience compression are the electrons, and their Fermi energy changes from about 10 keV to about 1 MeV when you get to about 10 to the 6 grams per centimeter cube. So electrons become relativistic, and the liberation is a phenomenon where they become ionized and they completely delocalize from the atoms. Between about 1 million grams per centimeter cube to about 10 to the 11 grams per centimeter cube, the electron Fermi energy now begins to reach nuclear energy scales, and it goes from about 1 MeV to about 25 MeV. So when the electron has energy enough to start changing protons to neutrons in a nucleus through the weak interaction, these electron capture reactions produce very neutron-rich nuclei in the ground state. Now, as you compress matter further, from about 10 to the 11 to 10 to the 14 grams, the neutron Fermi energy inside the nucleus begins to increase, and it gets larger than the nucleon mass. So this is the non-relativistic chemical potential, which without the nucleon mass goes from about 1 to 30 MeV. So at this point, the nuclei are so neutron-rich that they cannot hold on to the neutrons anymore, and the phenomena you have there is neutron drip. And once the neutrons drip out, we know enough about neutron interactions to predict that the neutron-neutron interaction, which is attractive, will produce a superfluid state of neutron matter. Now, as you go further from about 10 to the 14 to 10 to the 15 grams per centimeter cube, now the neutron chemical potential is getting very large, getting to QCD scales. And at this point, we expect that, first you're going to have dense nuclear matter, but at some point, the nucleon is not going to be a good degree of freedom because the chemical potential is very large, or alternatively, because the distance between nucleons is comparable to the intrinsic size of the nucleon itself. So the same thing that I described in a picture is shown here. What's shown is the evolution of matter as a function of depth. So what's shown on the left y-axis is the density in grams per centimeter cube, and on the right y-axis is the electron chemical potential, and the x-axis is just the depth. So as you compress matter, you can see that by the time you get into about 1 meter into the neutron star, you've already exceeded the densities, for example, encountered in white dwarfs, and you start having very relativistic electrons that transform iron, which is the most stable element in the outer regions of the neutron star, into very neutron-rich isotopes. And eventually you have neutron drip, and the neutron drip region is called the neutron star inner crust. And there is the likelihood that there are exotic shapes of nuclei encountered in the inner crust of the neutron star, where the neutron superfluid coexists with nuclei that can have rod-like or slab-like structures. And at about half the nuclear density, you expect a phase transition from crustal matter composed of nuclei to uniform liquid of neutron-rich matter. And then further deep inside the neutron star, new degrees of freedom are likely to emerge. So our current understanding of neutron star structure is depicted in this figure. As I just discussed, the very outer regions, maybe about 500 meters or so, is composed of nuclei and electrons, very relativistic electrons. The next kilometer or so is called the inner crust. It is a very interesting phase already because it contains a crust made of a lattice of nuclei, relativistic electrons, and non-relativistic neutrons that are forming a superfluid. And then there's the region where you have uniform liquid of neutrons, protons, electrons, and the electron chemical potential is large enough that you can also have muons present in the outer core of the neutron star. And then there's a density at which description in terms of nucleons breaks down. And so quark degrees of freedom emerge in some way. We don't quite understand how they do it. We have many models, and that region I depict as the quark-hadron transition region. It doesn't need to be a phase transition, but it could be. And there could also be a region deep in the core of a neutron star where quarks may be good quasi-particles. It doesn't mean that they have to be very weakly coupled, doesn't mean that they have to be a Fermi liquid, but they may be good starting degrees of freedom to describe matter at these high densities. So that's the standard picture of neutron stars, but ultimately we need to learn something about neutron star interiors and the matter and the properties of matter that contain by using observations. And the oldest game in town has been to use neutron star structure to constrain the equation of state. So the equation of state is just the relationship between the pressure and the energy density. And we know for many decades now that there is a one-to-one correspondence between the pressure energy density curve and the mass radius curve of neutron stars. So the only ingredients are general relativity to make this connection. And so this is the most robust way to connect observations to fundamental properties of high density matter. So there are certain trends one can see. So if you have an equation of state that is soft compared to the red curve at low density and stiff compared to the red curve at high density, then it produces a neutron star that differs from the predictions of the red curve, and that's shown by the yellow curve here. So if the equation of state is soft at low and moderate density, it tends to produce smaller neutron stars. If the equation of state is stiff, which means it just has a larger pressure, then it produces large maximum masses for neutron stars. So we've been able to use this correspondence between pressure and energy density to derive constraints on the equation of state of neutron stars. So for example, if we find a small radius from observations and a large maximum mass, what it implies is that there must be a transition from low values of pressure that can support a small radius neutron stars to very high values of pressure needed to support a very high mass neutron star. So that means that the pressure must change very rapidly at some intermediate density inside a neutron star. So here's a plot of the pressure versus energy density curve once again, and it shows various regions in the neutron star. at about 10 to the 14 grams on the x-axis is the separation between the crust of the neutron star and the core of the neutron star. All of the other points, relativistic electrons, neutron drip, neutron-rich matter are indicated there. Again, pressure is measured in MeV per Fermi cube, and the energy density is measured in grams per centimeter cube. So what we've learned over the last couple of decades is there are regions of the neutron star that one can calculate using nucleon degrees of freedom. And there are regions of the neutron star that one cannot. And here we need to rely on models and speculation that is often not validated by either experiment or controlled calculations. So I like to separate the neutron star into these two regions, the region where we have access, and I will specify what access really means more specifically. But this is a loaded statement that there are regions we calculate, and I'm sure there'll be questions about this. We can address this at a later point in the talk. When I say calculate, it means that there is a way of accessing the error associated with thermodynamic properties or transport properties of matter that you calculate. In a sense, it's the region where the speculation is needed that is more interesting, because that is the region where quarks may appear or new degrees of freedom may appear. But for most of this talk, I will restrict myself to what we can learn by using the calculations that can be reliably obtained by starting with nucleon degrees of freedom. So you can ask, what can we access with calculations of the nuclear equation of state? It turns out that the radius of a neutron star is largely determined by the properties of matter between about 10 to the 14 grams per centimeter cube and about 5 times 10 to the 14 grams per centimeter cube. So it's fortunate that radii of typical 1.4 solar mass neutron stars can be calculated using these methods. However, questions such as what is the maximum mass of a neutron star really require us to describe matter at the highest densities where nuclear degrees of freedom are not the best way to proceed. So from observations, we've learned that we've learned two important things in recent years. First is that massive neutron stars exist. So 2 solar mass neutron stars have been found in the last 5 or so years. So that provides very important evidence that the equation of state in the inner core of the neutron star must be stiff enough to support these large mass neutron stars. The radius of the neutron star, on the other hand, has been difficult to measure because traditionally these required an interpretation of X-ray observations to extract the radius by making assumptions about the spectrum of the radiation coming from neutron star surfaces. And this was always a difficult business. But nonetheless, attempts to extract the radius of the neutron star using X-ray observations suggested that the neutron star radii were typically between about 10 and 13 kilometers. Now, all of that changed when we saw gravitational waves from neutron stars, because it gave us a whole new way of measuring neutron star radii. So we've learned that binary Inspiral of 2 neutron stars produces gravitational waves. So the basic physics is that this oscillating quadrupole, time fluctuating quadrupole created by a neutron star in a binary orbit produces amplitudes for gravitational waves that can be detected up to about 100 or 150 megaparsecs. And advanced LIGO can detect about the last 100 orbits of such a merger for neutron star mergers out to about 100 megaparsecs. So the amplitude for these instruments is typically about 10 to the minus 23 in the strain, or 10 to the minus 24 perhaps in the next generation detectors. So this method of studying neutron stars using gravitational waves shows great potential. And we saw that we got very lucky with having a gravitational wave event at very short distance from us. It was just about 40 megaparsecs from Earth. And this gravitational wave emission from the first neutron star merger was able to provide us source parameters like individual masses to fairly good accuracy. For example, one of the masses that was measured was 1.47 with an error of about 0.13 solar masses. Other quantities, which are combinations of the masses, for example, an object called the chirp mass is measured to 3 decimal points. So this can become a precision science for measuring neutron star properties, especially their masses. However, the object of interest for us is not the mass of the neutron star, because there are other ways to measure it, and it doesn't provide significant information unless it's very large or very small. What we're interested in is the radius of a neutron star. So for close-by neutron star mergers, it turns out we can also measure the radius of the neutron star using a phenomenon known as tidal deformation. So because neutron stars have a finite size, when their orbital separation becomes comparable to the radius of the neutron star, then the tidal forces of one of the neutron stars deforms the second neutron star, and the second neutron star develops a quadrupole moment. And this quadrupole moment changes the orbital evolution of the system. And so this change in orbital evolution of the system can be measured, and the way you measure it is you calculate how does the rotational phase of the orbit change when you induce a quadrupole moment. And so the quadrupole moment of the neutron star is usually called the tidal deformability, the ability of a gravitational field to change the quadrupole structure of a neutron star. And the change in rotational phase is just proportional to the quadrupole polarizability of neutron stars. It turns out it's proportional to the quadrupole polarizability of both neutron stars, and that there's a very specific combination of the two neutron star quadrupole polarizabilities that enters in changing the gravitational wave rotational phase. And that's shown here in this expression. It depends on the masses of both objects, and it depends on the individual polarizabilities of both objects. So the most significant observation, which was made by several people about 10 or so years ago, was that the quadrupole or the tidal deformation of neutron stars is very sensitive to its radius. So the tidal deformation, lambda, is proportional to the quadrupole polarizability lambda, small lambda, divided by the mass to the 5th power. But that is proportional to the 5th power of the radius. So the larger the neutron star, the more easy it is to deform it. And K2 is a constant of proportionality, which depends to some extent on the density distribution inside the neutron star and has a weak radius dependence. But the dominant radius dependence is probably between r to the 5th and r to the 6th power. So this
Sanjay?
is, yes.
There is a question from the audience. What would be the time interval of the last 100 or so orbits?
The last 100 or so orbits will be on the order of tens of seconds.
Thanks.
Let's see, I'm going back here. Okay. So what we learned from analyzing the data from the first neutron star merger was that we did not see signatures of large tidal deformations in the signal. And that put a model independent constraint on the radius of the neutron star. So pretty much all the analysis we have to date suggests that this is independent of any models of the neutron star structure itself. It just relies on the fact that if the neutron star was greater than 13 kilometers, it would produce a large, it would have a large impact on the tidal, on the gravitational wave emission. So by not seeing any impact of tidal deformations on the gravitational wave emissions, you can derive a fairly robust constraint on the radius of the neutron star, and that number is about 13 kilometers. So this is beginning to suggest that this is probably the most systematic free observation that we have that tells us that neutron stars are small. And requiring the maximum mass of a neutron star to be greater than 2 solar masses also puts a lower bound in the neutron star radius, suggesting that neutron stars must be greater than about 9 kilometers. So here are some results obtained by 2 different groups. One of them involves the LIGO scientific collaboration, and another involves people working, nuclear physicists and gravitational wave physicists working together to extract radius and tidal deformation parameters from the first observation. Now, from a theoretical perspective, we know something about the nuclear equation of state, and we can include that information to learn more about neutron star tidal deformabilities. A part of the research I've been involved in and several others have been involved in is how do you combine information about nuclear matter at low densities and neutron star observations to gather new insights about dense matter and about neutron stars. So at lower densities where one can treat nucleons as non-relativistic degrees of freedom and where the typical Fermi momenta are not too large, we have used non-relativistic quantum many-body theory to describe nucleon-nucleon interactions. And here the two-body nucleon-nucleon potential is very well constrained by scattering data. The three-body potential is also constrained, but not as well, especially for the interaction between three neutrons. And the strategy in theoretical approaches to dense matter is to start with a Hamiltonian for nuclear interactions and derive the equation of state using quantum many-body theory. There are many different methods used. There are non-perturbative methods, numerical methods like quantum Monte Carlo. There's many-body perturbation theory, coupled cluster methods. What's interesting is that all of these methods that have been used to describe nucleon-nucleon interactions are providing consistent results for nuclear matter up to a certain density. And I'll discuss that in the next few slides. What was missing until maybe about 10 years ago was a way to estimate errors associated with these potentials between nucleons, because these initial potential models for nuclear interactions had to rely on ad hoc assumptions on the behavior of these potentials at short distances. But in recent years, the development of effective field theories, especially chiral perturbation theory applied to nucleons, has begun to provide significant guidance to these calculations. So what's happening with these modern nuclear forces is instead of making assumptions about the short distance behavior of these nuclear forces, you organize the Hamiltonian, you organize the operators that occur in this nucleon-nucleon Hamiltonian in powers of the momentum over a breakdown scale for the effective theory. So one uses the separation of scales between the light pion mass, which has a mass of about 140 MeV, and all the other heavier degrees of freedom, such as omega mesons, rho mesons, and others that contribute to the short distance behavior of the force. The separation between 140 MeV for the pion mass and say about 700 MeV for the heavier meson mass provides an expansion scale. And this breakdown scale lambda b is expected to be of the order of, say, the rho meson mass. Its precise value is more difficult to pin down, but the expectation is it's probably around 600 MeV. So as long as the typical momentum of the nucleons is small compared to this breakdown scale, you can calculate, you can organize the Hamiltonian in this power series of operators. And the beauty of effective field theory is that you can calculate using very few operators what the energy is. For example, at leading order in this Hamiltonian, there's a short distance force and a long range force due to pions. And you can calculate some observable, say the pressure of the system. And you can improve the calculation by including more and more operators. The other aspect of this calculation is that it gives you a hierarchy of 2- and 3-body forces, which is also very useful if you want to estimate how the errors grow as you make the matter density higher. So these developments, and there have been many people responsible for developing these effective Hamiltonians. Initially work started by Beer, Van Kolk, and Weinberg, but since then there are many people who have contributed to the development of these Hamiltonians. What the real advantage here is, it allows you to estimate errors and also gives you indications of when the effective theory breaks down. The effective theory breaks down when you can no longer have higher order operators contributing a smaller amounts to the observed quantities. So what's shown here is that as you increase the order of the calculation, you should see that the error in the object that you're calculating must decrease in a certain way. And when you see this convergence, you know that the effective theory is working. And when you don't see the convergence, you realize that your momentum scale is probably larger than the breakdown scale. So the equation of state of neutron matter has been calculated by many groups. This ab initio method has been around for more than a decade now. What I'm highlighting here is very recent results where the pressure of nuclear matter at saturation density and twice saturation density has been calculated. In the figure here, I'm showing pressure 1 sigma errors from a very recent calculation by Christian Drüschler and collaborators, and you can see that with increasing order in this chiral expansion, you continue to see convergence of this up to about twice nuclear density. And so at nuclear density, the convergence is certainly much better, but at twice nuclear density, you still see that the truncation of this Hamiltonian is not preventing us from using the calculation to calculate pressures. So what this table here shows is the pressure at saturation density and twice saturation density. And most importantly, what is the error? So these are the 1 sigma errors estimated from just looking at the truncation of this Hamiltonian. And you can see that while they are consistent, 2 different calculations, both based on effective field theory, there are important technical differences between them, but they're both fundamentally based on effective field theory descriptions. You can see that at nuclear density, the pressure's about 2.5 MeV with an error of about 0.7 or 0.7 MeV per Fermi cube. At twice nuclear saturation density, the error is a significant fraction. So here the error is almost 50%. And you can see that 2 different calculations produce pressures of the order of 15 MeV per Fermi cube. So what can we say about neutron stars, given that we know something about the pressure up to, say, twice nuclear density? We can go back to this little plot that I had that I showed you earlier and start putting error bars on the equation of state, and then ask, given these error bars in these equations of state, what can we say about neutron star structure? So even though we only know the nuclear equation of state up to, say, twice nuclear density using these effective field theory calculations, at higher densities, causality tells us that there is a maximum pressure you can reach because the speed of sound has to be less than the speed of light. So there is an upper boundary to whatever real theory of dense matter is at these higher densities that can access. At lower densities, at lower pressures, there is also an exclusion region created by the fact that you have a 2 solar mass neutron star. So the existence of 2 solar mass neutron stars requires a minimum pressure at these higher densities. And this minimum pressure tells us the existence of a minimum pressure and a maximum pressure combined tells us that there is a boundary on the uncertain region at high density. And we can explore this boundary either by parametrizing the speed of sound or by just constructing polytropic equations of state. And there are even methods to explore this region using a Gaussian process where you don't parameterize the equation of state, you just explore all possible scenarios. And one can do that, and by exploring all possible scenarios at these high densities, you can predict what are the mass radius constraints one can derive by just using information up to a certain density where you have calculations of the equation of state available. So that's what's done in this plot here. What's shown is the by combining neutron matter calculations. What's shown here is the mass versus radius. And I'm only using calculations up to nuclear saturation density. And then I use a general parameterization of the high density equation of state subject to this constraint that it must produce a 2 solar mass neutron star and that its speed of sound must be less than the speed of light. And you see that there is this large region that can be produced if you use what we know up to nuclear density. And this is already pretty constraining. You can see that neutron star radii must be greater than about 9.5 kilometers and should be less than about 14 kilometers. But if you now use the equation of state calculated up to twice nuclear density, you see a dramatic improvement in the predictions for the mass radius of a neutron star. So now, instead of the maximum radius of a neutron star being as large as 14 kilometers, the maximum radius allowed for neutron stars is about 12.5 kilometers. Now, this is interesting because we can use this information on neutron star structure coming from ab initio calculations of neutron matter up to twice nuclear density, combine that with gravitational wave data analysis, so that gravitational wave data analysis can use improved priors on the structures of neutron stars. And also the fact that the 2 neutron stars involved in the gravitational wave event have the same equation of state correlates the 2 neutron stars. So when you use the nuclear physics information up to about nuclear density, which we think is very conservative, and where the effective field theory certainly shows good convergence properties, one can extract a radius constraint from the gravitational wave observations that are significantly more stringent than the model independent constraint that said that the radius has to be less than 13 kilometers. So this is very, very interesting. It also turns out that in separate work done on the dynamics of neutron star mergers, that if the neutron star radius was very small, it turns out that the merger would produce a black hole promptly rather than have a significant time scale over which it could emit electromagnetic radiation. And the observation of electromagnetic radiation from the first neutron star merger places a somewhat model dependent, but still robust lower bound on the neutron star radius. And that's what that is what is depicted here. So based on observations of GW 170817, it seems very likely that the neutron star radius is less than 12 kilometers and is perhaps greater than about 10.5 kilometers. Now, unfortunately, if you look at this plot here, the 2 neutron stars in the neutron star merger have masses and radii that would be compatible with an equation of state that was smooth. But in the future, if we can measure the tidal deformabilities and extract the neutron star radius even better, to say a few percent, then there is the possibility that you would discover neutron stars that cannot be connected by a smooth equation of state. So if the variation in radius for a small variation in mass is very large, that would require a very rapid change in the pressure with increasing density. And that would be a direct way to measure the possibility of a phase transition at higher densities. So I should also mention that very recently, in the last few months, there's been a new approach to measuring neutron star radius. And this new approach is based on looking for hotspots on neutron stars. And these hotspots on neutron stars provide a measure of the geometry of these neutron stars, because light bending plays an important role in
Sanjay?
determining. Yes.
Sorry to interrupt. Veronica, go ahead, please ask the question.
Sorry to interrupt you, but I had a feeling that you're changing the topic a little bit. Can you go back 2 slides? I just had a question about one more, yeah. When you, forward,
Okay.
Forward. There, you inserted an overlay now, right? For when you include the constraint for the 2 times saturation density.
Yes.
My question was, around there, the hyperons are expected to appear, right?
Right.
Is there any
So
way you could quantify the extra error that comes because of that?
yeah, so between 1 and 2 times nuclear density, there is the possibility of new degrees of freedom appearing. You could have hyperons, you could have pions, and at the moment, we don't have a good way of quantifying the error associated with that. What we do know is if the EFT is breaking down, we can estimate those errors. The errors associated with the phase transition, we cannot. And that's where we have to use observations. We have to use observations because we don't have a reliable way of calculating hyperons or pion condensates. One would like to see, is this prediction compatible with nature? If it's not compatible with nature, then one would ask whether we need other degrees of freedom to account for it.
But I was just trying to think if this curve will go right or left if you had hyperons, right? Because
It'll
your
go to the
gradient
left.
state would get
It
softer.
will go to the left. It'll make it softer.
Okay, thanks. So it'll make it even smaller. Okay.
It'll make it even smaller. So coming back to this question, in fact, if you observations of two neutron stars with small radius uncertainties might point to a phase transition such as the one you just mentioned. It is possible that we will learn from observations that there is a softening needed, but at the moment we don't have the data to direct us in that in addressing that question. So, so the NICER is another way of measuring neutron star radius, and it measures neutron star radii by looking at the emission of hotspots around neutron stars. I don't have time to go into details of this, but the analysis of these X-ray profiles, which basically tell you how light emitted from a hotspot travels around the neutron star, gives us constraints on the compactness, which is the mass over radius ratio. And analysis of the NICER data is actually consistent with the analysis done for GW17OH17, although it favors slightly larger radii as depicted by these ellipses here, but also with much larger errors. So I would, at the moment, I would conclude that, you know, the gravitational wave observations are certainly very constraining, much easier to interpret, and the NICER observations are a little bit trickier to interpret, and they rely more on our assumptions of understanding how these hotspots form and what their locations are, etc. But taken together, I think they're suggesting that neutron star radii are probably around 12 kilometers and not likely to be around 14 kilometers. Now, a small neutron star radius has important astrophysical implications. It impacts the interpretation of X-ray emission from neutron stars. It has a direct influence on the size of the neutron star crust. It impacts, for example, the maximum mass of neutron stars and the dynamics of neutron star mergers. So knowing the neutron star radius as to whether it's less than 12 kilometers or larger than 13 kilometers has direct implications. One really fascinating implication is that the radius of the neutron star seems to determine whether or not you can have electromagnetic emission from a merger of a neutron star and a black hole. So that's what's depicted here in the figure, where the ability to produce electromagnetic signals from neutron star black holes depends entirely on whether or not you can disrupt the neutron star and eject matter before it is consumed by the black hole. It depends on the simulations, of course, but the simulations done to date suggest that it's a very strong function of the black hole spin, which is represented on the y-axis, the black hole mass, which is represented on the x-axis, and the neutron star radius. So anything to the left, to the top left corner, is simulations that would produce electromagnetic radiation. And what this figure is showing is that if the neutron star radius, for example, is between 10 and 12 kilometers, then either the black hole needs to be spinning very rapidly, or the black hole mass needs to be very small in order to produce electromagnetic radiation. So our conclusion from this study was that if black hole spins are small and black hole masses are greater than about 5 solar masses, then it's very unlikely that neutron star black holes will produce electromagnetic signatures if the radius is less than 12 kilometers. So a very large neutron star is easy to disrupt, but a small neutron star would be hard to disrupt, and that would have implications for multi-messenger observations of neutron star black hole collisions. So that's the astrophysical implication. What are the implications for dense matter? It turns out that there's an interesting implication for dense matter. The small radius of a neutron star combined with a large maximum mass, as I mentioned earlier when I was discussing the relationship between pressure, energy density, mass, and radius, is that a large maximum mass and a small radius suggests that the pressure must increase very rapidly somewhere in the core of the neutron star to be able to support both of these observations. Now, since the speed of sound squared is just the derivative of the pressure with respect to the energy density, what these observations are suggesting is that the speed of sound likely exceeds this value of 1/3, which is what you would get if you were to calculate the speed of sound at very high density using perturbative QCD. So it implies that the speed of sound must be non-monotonic, because it has to rise above this value of 1/3 to be able to support the 2 solar mass neutron star. And so given these two simple scenarios shown in this plot, it looks like the scenario shown in the blue curve is what the data wants, and a simple, smooth, monotonic increase of the speed of sound in dense matter from densities which are nuclear densities out to very high densities where we know quark degrees of freedom are present, cannot be smooth. It must have a maximum somewhere in between. The exact shape of this curve is not known. It could have, there are several possibilities that would all satisfy the observations, including what's shown here in this cartoon. There could also be a curve in which one has a first order phase transition where the speed of sound increases to some value, and then there's a first order phase transition before it transits into some form of quark matter. Now, there has been speculation in the literature that the speed of sound in many theories does not exceed 1/3, and perhaps maybe that is true also for dense QCD. And if you look at the speed of sound in QCD at finite temperature, one sees interesting features. For example, lattice QCD, which can provide reliable calculations of the speed of sound. The results from these lattice calculations are shown in this plot. You can see that the lattice calculations from two different groups, the HOTS QCD collaboration and the BMW collaboration, show that the speed of sound approaches 1/3 from below, and at densities close to the critical temperature, at finite critical temperature for the QCD crossover, which is about 170 MeV, you see a non-monotonic behavior where the dynamics is very complex, and it seems to resemble the predictions made from hadron resonance gas models, where the pressure due to pions first increases the speed of sound, and then contribution from heavier mesons being produced as you increase the temperature leads to a decrease in the speed of sound. But in this case, you see that the speed of sound remains to be less than 1/3. So the interesting example here is, I'm showing this interesting example because you see non-monotonic behavior when there's a change in the degrees of freedom, and which may in fact be happening in the neutron star core as well. And I also show this because this is an example in which a QCD seems to show that the speed of sound is less than 1/3. However, I also in recent days learned that there is a simple phase of QCD where you can do controlled calculations and where you find that the speed of sound exceeds 1/3 without violating any known physics. And that is a QCD at finite isospin density. So a QCD at isospin density can be calculated. It doesn't have a sign problem. You can calculate what the speed of sound is using lattice QCD. And you can also calculate it using chiral perturbation theory. And it turns out that a comparison between chiral perturbation theory and lattice QCD was found to be in remarkable agreement. So this plot here shows the speed of sound in a pion condensed phase of QCD matter, where as you increase the chemical potential, you produce pion condensate. And this pion condensate has a very large speed of sound. And the speed of sound in this pion condensate in leading order chiral perturbation theory is just given by the simple expression. So even at relatively low density of pions, one has this very large speed of sound. Okay, so I have grossly misjudged the amount of time I would need to go through all of these topics. So what I'm going to do is try to, I'm going to have to skip a lot of what I wanted to talk about and maybe see how much time I have left from Igor before deciding what I skip.
Well, you are free to go for the next 10 minutes if you'd like.
Okay, so so let's see. I'm going to skip over some aspects of the accreting neutron star physics, and I will spend maybe the next 10 minutes talking about neutron star mergers. I'll try to keep this short. I won't go 10 minutes. Maybe I'll go 5 minutes. Let's see how it goes. So the other aspect of neutron stars that is interesting now is the study of neutron star mergers. And for obvious reasons, because gravitational waves are providing us the, useful data. So the merger of two neutron stars, you can think of it as a general relativistic heavy ion collision. It's in many ways, it is the ultimate collision. It is a collision that, produces the hottest and densest state of matter in equilibrium. And it is also the collision that produces a black hole. It very likely produces the heavy elements. And what this animation here is showing you is the different stages of the collision of these two neutron stars. So what you're seeing is the late stages of the Inspiral, the collision, ejection of matter, and nucleosynthesis of very heavy elements is expected to occur in this ejecta. So these components or these phases of the evolution are actually being confirmed by observations. The Inspiral of the two neutron stars was observed in gravitational waves as depicted in the figure here. I'm just pointing to how the frequency of the gravitational wave increases up to the collision point, and this is known as the chirp, as the frequency increases as the neutron star gets closer together. About 2 seconds later, there was a gamma ray burst associated with the merger. And then on time scale of days, the matter that was ejected produced electromagnetic radiation. Now, all of these stages of neutron star merger dynamics, it's a very complex numerical relativity simulation that is required to actually predict observables, but it relies very heavily on the equation of state of matter at very high temperature and at high density. So this is an interesting collaboration between astrophysicists and dense matter physicists to try and connect what we observe to what might be the properties of matter inside these merging objects. So the interesting dynamics is the merger phase where the two neutron stars are disrupted. During this disruption, you can produce neutron star oscillations, you produce a lot of ejecta, and this ejecta likely produces the nucleosynthesis. So I will just skip right to why this is interesting. It's interesting because the ejection of material appears to depend on when the matter is ejected. There seems to be two types of ejected material. There's the material that's ejected at early times, and this material that's ejected at early times really remembers the neutron-rich conditions encountered inside the neutron star. And then the ejecta that comes at later times, that is the ejecta produced by shocks in the collision, is exposed to a very large amount of neutrino luminosity produced by the hot and dense matter. And these neutrinos are very good at changing the composition of matter. They take neutron-rich matter and convert some of the neutrons into protons, so they decrease the neutron richness of this matter. So the amount of neutron richness in the matter being ejected is critical to understanding nucleosynthesis. So the amount and composition of the material ejected depends on the dynamics of the collision, how long does the merged object live, how quickly does it emit neutrinos, and also on other properties such as the maximum mass of the neutron star and the neutron star radius. So to make heavy elements, it turns out you need to make heavy elements such as plutonium and uranium. You need very large neutron excess. And this very large neutron excess, in excess about 85%, is needed to make the heaviest elements. So what's shown here in this little animation is you start with some nuclei in this region where they're not very heavy, and as you allow them to evolve, neutron capture reactions and beta decay reactions produce a wealth of heavy elements, which then decay back to stability. So when they decay back to stability, they emit a lot of electromagnetic radiation that can be observed. So these electromagnetic curves that we see from neutron star mergers called kilonova provide us very important information about the dynamics of the merger. So robust synthesis of heavy elements indicates that very large neutron fractions were observed. It also indicates from observations that the type of material produced in GW1708-17 must have a combination of both elements, very heavy elements that were produced that started out neutron rich, and not so heavy elements, ion-like elements that were produced that started out neutron rich, but which were then processed by neutrinos to make them less neutron rich. So because I'm running out of time, I just want to mention that the observations and the modeling of these observations, just the electromagnetic observations, was able to provide very useful constraints on the amount of matter ejected. So I want you to just focus on the fact that what I'm showing at the bottom of the slide, the light curves require about 0.04 solar masses of material to be ejected, which produced very heavy nuclei, and about 0.025 masses of material was ejected that produced the lighter nuclei. So we have constraints on the composition and the amount of ejecta, and this is probably a very good diagnostic of what is going on during the post-merger evolution of these neutron stars. Now, there is one fascinating aspect to this observation, and it tells us that if you want to extract a few percent of the mass of a neutron star, you really have to get rid or blast out the outer 2 kilometers of each neutron star. So these heavy elements that were being produced actually came from neutrons and protons that occupied the outer 2 kilometers of the neutron star. And I remind you that most of the outer 2 kilometers of the neutron star in mass is contained in this inner crust where neutrons are in a superfluid state. So this is a fascinating example of what we've learned from neutron star merger observations. We've learned that most likely all the heavy elements contain neutrons and protons that were once in a superfluid state inside the neutron star crust. And in the future, if we see more of these and we see how the composition and amount of material changes, we will be able to diagnose better what was the merger dynamics. Okay, so I think I should, unfortunately stop here because we are already way out of time. I'm not going to be able to say much about dark matter, but if there are questions afterwards, I'm happy to address it. My apologies. But let me just put up my conclusion slide and take questions. From what we observed very recently, it looks like neutron stars are poised to play a very important role in astrophysics, especially in astrophysics involving gravitational wave observations. We've learned quite a bit about neutron star interiors from recent observations, especially about the fact that the equation of state probably stiffens very rapidly in the neutron star core. Neutron star merger is a fascinating opportunity for dense matter theorists and for astrophysicists. It has very many implications for both astrophysics and for nuclear physics. Interpreting these multi-messenger signals is not going to be easy. It is going to require a combination of computational astrophysics and nuclear physics, but I think there's a significant discovery potential. Thank you, and my apologies for going over.
Well, thank you very much for a very nice presentation. I actually regret that I only gave you 10 minutes to finish. It was very interesting, and I would rather listen for another half an hour. But let's give a chance to people to ask questions. So Jamie, please.
Hi, yeah, thanks for this very nice talk. So I think I have several questions, but I'll choose my favorite one, I guess. So the tidal deformability is playing an important role for larger mass stars, right? So we need to observe something that has a larger mass in order to see, I guess what I'm trying to say is when we observed GW170817, we didn't get all of the information that we need. Is that correct?
Yeah, so the tidal deformability is a strong function of the neutron star radius. It's a relatively weak function of the mass. Typically,
okay,
the bigger the mass, the smaller the radius. So what happens is the more massive neutron stars have lower tidal deformability. So if we want, what we would like to see is what would be ideal to measure the tidal deformability is to have a very light neutron star. Of course, if you measure the tidal deformability of a heavier neutron star, it gives us information about higher density matter.
Okay, that answers your question?
Yes, thank you.
Okay, so next, Henry De Jong.
Hello, I have a question. Can a hypermassive neutron star exist? What do you think their structure would be? And for how long could they exist?
So the hypermassive neutron star, the existence of a hypermassive neutron star depends on the maximum mass of neutron stars. So if typical neutron stars that are colliding have masses of order 1.4 solar masses, then it seems very unlikely that hypermassive neutron stars will exist as stable configurations. If, on the other hand, if you have two neutron stars that start out as one solar mass neutron stars, then they will produce a hypermassive neutron star that will be stable, because we already know that the maximum mass of the neutron star exceeds 2 solar masses, and some amount of matter is ejected during the collision. So it depends on the initial neutron star masses. But since most neutron stars we see are around 1.4, the typical neutron star merger is going to make a black hole. The time scale over which it makes the black hole can depend on a lot of input physics, but the most important one will be what is the maximum mass and how long does it take for the merged object to lose its angular momentum. So usually the time scales are of the order of tens of milliseconds if the initial neutron star masses are about 1.4 solar masses.
Thank you.
Okay, I have two more questions. One of them is coming from Mohammed Yunus. He has problems with internet, so he asked me to ask you a question. How to correlate heavy ion physics experiments and neutron star observation so as to constrain equation of state for finite size systems?
For finite size systems. Okay, so maybe what I should show you is this figure again. So there is clearly a region at moderate baryon density and high temperature shown here, which can be accessed both in neutron star mergers and in heavy ion collisions. Precisely what that region is and how reliably they can be extracted in heavy ion collisions is an open question. I am not an expert on it, and there is active work going on. For example, if we could figure out what the pressure of matter was at 50 MeV temperature and twice nuclear density from terrestrial experiments, that would be a fantastic input for studies of neutron star mergers.
Okay, next question, William Lynch. Hello, William?
Oh, yeah, okay, so I was muted. Okay, so can you hear me?
Yes.
Yeah.
Okay, so Sanjay, in your recent paper, you discussed the role of pions, specifically negative pions, in matter around 1.5 saturation density. If you go to higher order in the interaction or to higher densities, deltas can be quite important, and there's a sensitivity to the delta potential in the matter. So where would you think this would be most strongly observed in the case of neutron stars? In some cases, it was really quite key to the pressure, but it also could be relevant to the thermal heat capacity. And where do you think the sensitivities really are?
Right. So, I only had time to talk about the equation of state. The role of new degrees of freedom on the equation of state has been studied. Usually they soften the equation of state. If you introduce more degrees of freedom, they soften the equation of state. And the extent of softening usually is very model dependent. However, new degrees of freedom can have a much bigger impact on the transport properties of matter. Things like thermal conductivity, viscosity, neutrino transport. So in my opinion, the most promising way to study the existence of new degrees of freedom at very high density is to find observables that you can connect to transport properties of matter in the core and then extract them. So that's a whole nother talk. There are, for example, neutrinos from a galactic supernova, the lifetime of a merger. All of these depend sensitively on the transport properties of high density matter. And that gives you a way of also, the signatures of new phases are probably more robust there.
Okay, other questions from the audience? I do have at least one question of my own. I wasn't planning to interrupt unless there were more questions running from the audience, but I have a question regarding the NICER analysis. Essentially, you were saying and showing that picture that the tendency of the data to have larger radii than it seems from the, for example, merger events. Is the reason for that that when you are considering hotspots that they are basically only taking small area of the star and the size essentially appears to be much larger? And does it mean that there are some inherent sort of wrong assumptions about the hotspots?
No, so, well, the hotspots, the size of the neutron star is coming from the amount, there are various effects on the light emitted from the hotspots. The analyses considered several different shapes for the hotspots, 2 hotspots, 3 hotspots. There's enough, the data constraints, you don't have a lot of freedom in choosing these hotspots. It's fairly well constrained. Of course, it's computationally very difficult to explore all possible hotspots. So that's a systematic error. However, it's, they've done a fairly careful analysis of changing the hotspot size, the shape, the temperature profiles to see what fits the data best. And these larger radii are, when they have different numbers of spots, for example, the radius changes. So the systematic error associated with changing the number of hotspots and the shape of the hotspots, etc., needs to be studied. And once we know that, you may end up with smaller radii. I don't know.
Okay. So thank you. Any other questions from the audience? I don't want to hijack this all by myself. So if there are no more questions, first of all, I would like to thank Sanjay for agreeing to give a talk, for an attempt to give it really, really nicely with accessible information that everybody understands. I greatly appreciate that effort. And I think this is the time we should thank all Sanjay, and we will be wrapping up.
Thank you, everyone. Thank you for your patience.
Okay, thanks everybody.